Yeah, I guess we can start. So as I just explained, so my intention is to cover like almost everything that's left for the exam, like this week. Definitely, the final exam is on Wednesday of next week. I'll send you the study guide probably today or tomorrow. Um, but I don't want to like cover new stuff on Tuesday. Preferably, I would also try not to cover like new material on Monday of next week, so that we can just do more like practice problems or things like that. So I'm trying to kind of wrap up the material by this week. So because of that, like the quizzes, like instead of quizzes, I'll like for the last two remaining quizzes, I'll do kind of something similar where I just will give you like four problems to work on by the end, and you just submit them by some over the weekend or something like that. I'll send you that assignment also today or tomorrow. But and that's kind of I feel better so that we can try to wrap up the material this week and let you have like a full weekend to study for the final. Um, so that's kind of my plan. So yeah, no quiz today, and the last quiz is also no quiz. No quizzes this week. I'll just do like an assignment instead for the two that were left over. I also tried to grade the exams um, today. Between today and tomorrow, I should have like the uh, grades for the exam of yesterday. For the final exam, also uh, yeah, basically homework two will be counted as two homeworks, two quizzes and homework. I mean, the last homework will also count as two quizzes. Um, for the what I was going to say is that for the final exam, I'll give you some formulas. So I'll let you know because at this point of the course, like there are a lot of different formulas by the end of the semester, by the end of the course. I'll give you like a list of formulas so that you don't need to memorize. Um, I'll write those on the study guide. So those you will see on the exam, so that you don't have to memorize them. Yeah, I don't think. Yeah, like sometimes I leave that option of a homework grade in case I wanted to like do something else. But yeah, if I don't have anything, I'll just give everyone those points. Uh, Basically, it was more like just in case I thought, oh, maybe I'll do as something specific. But yes, sometimes I have used it to make people watch it like a YouTube video and answer questions about that, things like that. Uh, But yeah, the course is still 500 points. The only thing I would do is like just give everyone those points if we don't end up having that any homework there. Yeah, it's still 500 points. Um, so let me tell you today. Today we have to talk a little bit about the dot product. We had seen that before very briefly, but I had not like we had not gone into too much detail. So what was the idea of the dot product? Well, you have two vectors, um, U and V. Uh, for the dot product, you need the both vectors to have the same number of entries. And then the formula for the dot product was that you multiply the entries, the first entries, the second entries, the third entries, the fourth entries, you multiply them together and you add up all the numbers. So just to give you some examples, what was the dot product here between u and v is like, well, -1 plus 0 plus 15, right? So that gives, that's what you get if you if you multiply these entries together and then you add the answer, that's what you get. And so that gives you 14. And then, I mean, it is the same formula regardless of the number of entries of the vectors, right? So it's kind of like easy to manipulate. The only thing that you do need is for all the vectors to have the same number of entries. So here u dot v would be -2 plus 2 plus 0 plus 9, which is 9. Okay. So so let me just tell you the really important stuff that you need about the dot product. Oh, the other thing that is kind of useful, which we had done before, if you remember, this was like a problem a long, long time ago. But the problem was you had a vector, let's call it v, which was xy. By the way, in this formula of the dot product, it doesn't really matter whether you have the vectors as rows or columns. So you can write it as rows, or you could also write the vectors as columns. It doesn't, like, for doing the dot product, that doesn't really matter. So if you remember, when you have a vector xy, you could rotate it by 90 degrees, right? So this is, let's call this u, which, if you remember, like, we had found like a formula for the vector rotated 90 degrees. So to do that, you can just use a matrix, the rotation matrix, to find a new vector. But let's just believe me that this was the new vector. So this is like the vector v. Well, if you look at the dot product between these two vectors, right, what do you get? You get xy dot um, minus yx, and this gives you what? Like if you write them as columns, it is the same formula. It's just that um, you you still do first entry with first entry, second entry with second entry. So there's nothing that changes in that formula. Okay. So why is this useful? Why is, and this is kind of like the property that makes a dot product like an interesting operation, because these two vectors were at 90 degrees or perpendicular, and that is more or less true regardless of the number of entries. So if the dot product between two vectors is 0, the vectors u and v are perpendicular. That's kind of like the key fact of the dot product, or the key property of the dot product. if two vectors U and V are perpendicular, meaning that they're like 90 degree, like, well, it could be 90 degrees, yeah, basically 90-degree angle. So the angle between them is 90 degrees. Then U dot V equals 0. Likewise, if the U dot V is 0, then the vectors were perpendicular. So it goes both ways. Likewise, if U dot V, then the vectors are perpendicular. So the point of this is that the dot product is a way, like the idea of the dot product, what makes it useful is that it is a method to detect whether two vectors are perpendicular or not. So if you want to know if two vectors are perpendicular or not, you have to take their dot product. And if you get the number 0, that means that they were perpendicular. So just to give you an example, let's say you take U to be, let's do -1, 1, 2, and V to be, let's see, -2. Does this one work? Let's check if this one works. So if you do this one, what happens if you do the dot product? Again, like it doesn't matter too much if I write them as rows or columns for computing the dot product. It's just that it's easy, it takes less space if you write them as row vectors. But if you do the dot product, you get -2, right? You get -2 -4, right? Plus 6. That gives you -6 plus 6, that's 0. Oops. So what that means is that U and V are perpendicular. I should be able to show you how these vectors look like so that you see that it is like, it does match like with how you would expect that to look. So let me see if I can go to the 3D graphic view. Yeah, so let me see if I can put them on GeoGebra. Yeah, so like for example, the first vector is U, which is 1, 1, 2, and the second vector, which I'm calling V, is -2, -4, 3. Okay, and I don't know, I mean, how clear it is. Let's see if I can make it. Okay, yeah, I don't know how clear it is. Like, if you look at it from the right perspective, let's just okay. If you look at it from the right perspective, it does look like the angle between these two vectors is 90 degrees. Okay, so of course, like in general, like once the vectors have more than 3 entries, you cannot easily visualize what's going on. But the idea is like if you had a vector with 4 or more entries and you compute its dot product with another vector and it gives you 0, you should still think that those vectors are somehow at a 90-degree angle. So the dot product is kind of like a very useful algebraic way of checking that two vectors are perpendicular without having to kind of draw them or do anything like that. Okay, so that's kind of how it looks in general. And then, okay, so that's one reason why the dot product is useful, because it allows you to check if two vectors are perpendicular. And the other reason why it's useful is because it is also related to the length of a vector. So let me just write that down, show you how this looks like in a couple of special cases before giving you the formula in general. So like imagine that you know, you have this vector, you have a vector xy. Well, if you have a vector xy with two entries, you can draw a right triangle where this vector is like the hypotenuse, right? So the length, right, like the length of the hypotenuse, well, it's just Pythagoras theorem, right? Like Pythagoras theorem says that it is the square root of the side squared. Okay, but then how could you get? The question is there a way to get x squared plus y squared from the dot product? A formula, and there is if you take the dot product of the vector with itself. So if you take the dot product of v with itself, v dot v, what happens with that? You get x squared plus y squared, which is exactly the stuff inside the square root. Okay. So, and that again is more or less true in general. So the length of a vector is actually the square root of the dot product of that vector with itself. So let me just write it in as a formula. So the length of a vector, this is like the notation that's used for length of a vector. Notation. It looks like an absolute value. It's called the length of a vector. Sometimes it's also called the magnitude of the vector or the norm of the vector. Also called norm or magnitude of a vector. But I'll just keep using the word length because maybe it's more natural. But the formula with the dot product is that the length of a vector is just the square root of the dot product of the vector with itself. So just for example, when so if V has like two entries, then the length is just like what I just wrote, x squared plus y squared. That's what you get if you do the dot product of V with itself. If V has three entries, then the length of V is just square root of x squared plus y squared plus z squared. That's what you get if you do the dot product of V with itself. Okay. And like it continues to work with more entries. So if V has like, for example, 4 entries, then the length of this vector would be like x squared plus y squared plus z squared plus w squared. So the nice thing about the dot product is that it has like kind of can be used to find the length, and at the same time can also be used if to detect whether two vectors are perpendicular or not. So it has like two purposes basically. So let me write that down. So here are like the key properties of the dot product that you need to know. is the first one is the one that I just had written before, that if the dot product of two vectors is zero, then the vectors are perpendicular. If u dot v equals zero, then u and v are perpendicular. Again, this is sometimes called orthogonal. That is like a word I may use. Every time I use the word perpendicular, I also use orthogonal in parentheses, so that to remind you that those are like synonyms. So perpendicular vectors are also called orthogonal. Okay, so this is like I'm putting that one first because that is probably the most useful property of the dot product, that it can be used to check whether two vectors are perpendicular or not. Like we'll use that a lot of the, like in what remains of this class, you'll see that it will be used multiple times. So this is really like the most, if you just remember this one, you're more or less remembering the most important property of the dot product. That really is the stuff that makes the dot product interesting. Okay. The second one is that the dot product, the square root of the length of a vector can be given in terms of the dot product. That one is this useful, but I mean that like it's more like as a fun computational way to check that. Like the other way in which this is written, which is a little bit more convenient, is that the length squared equals the dot product of a vector with itself. Like, if you square both sides of this equation, you just get this. This is a little bit better to compute. And the last one that we need to have in mind is that kind of the dot product is distributive. So if you have like a dot product between u and v plus w, you can kind of distribute the dot product in the same way that you would do, like it is like an ordinary multiplication in that sense, that you can just distribute like do this with this, and then this with that. It's just that it's with dot product. And the last one, oh, maybe I should say it explicitly because, right, it's maybe not so obvious. I mean, once you see it in terms of like the factor formula, it kind of is clear. But it like the dot product, it doesn't matter in which order you do the operation. So u dot v equals v dot u. Okay. So yeah, in order of importance is like it can be used to check that two vectors are perpendicular. It can also be used to find the length of a vector, and then like more like when doing actual computations involving dot product, that you can distribute it. That's nice to know, and that it doesn't matter in which order, like just like regular multiplication, it doesn't matter in which order you write the factors. That's kind of useful to write explicitly because this is not something we'll do in this course. But if you take multivariable calculus, for example, you'll see the cross product, and for the cross product, the order does matter. U cross v is not the same as v cross u, but that won't happen here. So for us, the dot product is always, you know, the dot product is always the order is fine, like if you multiply them. Is that okay? Are there any questions about this so far so good? Um, uh, well, there is a formula of the dot, right? There is a formula of the cross product that can be given in terms of matrices and the determinant. Um, if you do like, if you know that formula, then there was this property that when you swap the order of the rows, right, the determinant changes sign. So that corresponds to in the cross product that if you swap the order of the factors in the cross product, it changes sign. So so in a sense, yeah, in the sense the cross product it is some sort of determinant, although it is a little bit more tricky if you um because it's not a number, right? Like the determinant, like way we thought is a number. Um, if you see this formula of the cross product in terms of determinants, you have to put ijk in the, for example, in the top row to get a vector. So it's a little bit more. It is related to the determinant, but it's a little bit more subtle. Uh, but it's not the determinant of two matrices. It's like it's a bunch of like it depends again on how you write it, um, but yeah, there is a formula with a determinant for the cross product. But you'll see, like if you take multivariable or even like a physics one class, you'll probably be given that formula. The thing is that we don't have any purpose, any uses for the cross product in this class, so that's why I won't go into it. Like the dot product is a lot more useful than the cross product in general. Um, is that okay? But yeah, it is true. Like somehow we have seen parts of it because there's like a formula in terms of the determinant for that. Now, why? Okay, so why did I give you this stuff about the dot product? Because with the dot product, we can find something that's called a complement to a vector space. So let me tell you what that is. So this is like what we're going to do now. It's called the orthogonal complement to a vector space. And you'll see it's very, very easy to find. Uh, so let me give you like an idea of what this is. So like think of your vectors. Like let's say you have like a vector space V. Um, and I'll make it very concrete. Let's just say that your vector space is the vectors in 3 dimensions, right? X, Y, Z, like the vectors with 3 entries. So here's an example just to make it concrete. Okay. So let's say that your vector space is just given by this definition, like this. So it's all the vectors with 3 entries that satisfy that x plus y minus z equals 0. Okay. So this, like I think I have mentioned this a couple times before, that is really like the equation of a plane. Okay. So the equation, it does correspond to a plane in 3 dimensions. So like it's just like I have to draw it somehow, but um let me draw something like this. Okay. And it has a basis. Like again, a vector space can have many different types of bases. So we just need one. Uh, like this is kind of like the sort of thing that we covered for the second exam, right? You know how to find a basis for this vector space. Like for example, you could say that z equals x plus y, right? And then you say x y z is x y x plus y, right? Hopefully this looks familiar to everyone. Right. So a basis for B. What is a basis for B? It's two vectors. Has two vectors. The first vector is let's see. Let me delete this one. One vector would be, let's call it V1, would be 1, 0, 1, and V2 would be 0, 1, 1. Okay. So that's like a basis for V, these two vectors. So let me show you how that looks like on GeoGebra again. And let's see if I can pull it out here. Okay. Let's see. So if you let me put something like this. Okay. So if you go to GeoGebra, you can put like the equation x plus y minus z equals 0. That gives you a plane, which is what I was telling you. Let me see if I can change the color here for here it is. So that it matches like the color that I'm using on the iPad, on the tablet. So you have like this plane, and then the thing is, like in GeoGebra, it's harder to call the vectors v1 and v2. So I'm just going to call them u and v. Or I don't know if yeah, it won't let me call them. I'll call them v and w, just so that it doesn't gets confused with the other one. So one vector is there, that black vector, and the other vector is w, which would be 0, 1, 1. Okay, so hopefully yeah, maybe it's better if I draw them here. Like if you look at these two vectors, they belong to the plane, and they are a basis for this plane, right? So every other vector on the plane, the point of them being a basis is that every other vector in the plane is a linear combination of these two. Okay, that's the idea of a basis, right? That every other thing is like a linear combination of the basis vectors. Okay, so far I haven't told you anything new. This is like what we have been doing up to very recently. What's going to be the orthogonal complement? The orthogonal complement of the vector space is going to be all the vectors that are perpendicular to every single vector of B. Okay, so let me see if I can show you what I mean by that. So what is going to be the perp? That's how you say it, the perp. So what is the orthogonal complement? Well, this consists, by definition, you pronounce this as the perp. The idea is that this symbol should remind you of the symbol for being perpendicular. So that's why you put this symbol here. What is vperp? Vperp is all the vectors v, or let's call them u, because otherwise it would be a mess. All the vectors u, all the or the vectors u, which are perpendicular to every vector of v. So just like to make a picture here, before we had like V, which was like this plane. Oops. So that was V. What is V perp? What is V perp? Let me use green for that. V perp consists. I should probably delete this, otherwise it will look too weird. So V perp consists of all the vectors which make a 90-degree angle with every single vector in V. So you have like a vector in V, you have a vector in V perp. And every vector in V perp is perpendicular to every vector in V. So just to make you, maybe it's better if I do it with the actual physical thing. If you look at me right now, think of the plane as a piece of paper, literally, and V perp would be all the vectors that have like a 90-degree angle with the vectors in V in the plane. Okay. So it's like it's not that you're perpendicular to just one vector on V. You're perpendicular to every single vector of V. Is that making sense? In particular, what does if you are in V perp, right? If you are in V perp, that means that you must be perpendicular to the basis vectors because you are perpendicular to every single vector of V. So in particular, you are perpendicular to a basis. So in particular, this means that if you belong to V perp, then you must be perpendicular to every every basis vector. Is that making sense? So every basis vector of V. So let's just make this concrete. What does that mean in our example? So in our example, what does this mean? What does this mean for our example? Well, again, V was x, y, z, where x plus y minus z equals 0. The basis was V1 1, 0, 1 and V2 0, 1, 1. So what is V perp? Now V perp consists of the vectors. It will require the vectors, let's call them U, X, Y, Z, where U has to be perpendicular to V1 and U has to be perpendicular to V2 because it has to be perpendicular to every basis vector. What was the way to check that two vectors are perpendicular? That their dot product must be 0. So the condition for being in B perp can be translated into the dot products between the vector U and the basis vectors, the dot products, those dot products to be 0. Is that making sense? But what is the dot product between U and V1? Well, U is like XYZ. And V1 is 1, 0, 1. So this dot product must be 0. And U is XYZ and V2 is 0, 1, 1. And this dot product must be 0. So what I'm saying is that V perp consists of the vectors that were like, x plus z equals 0 and y plus z equals 0. Is that okay? So far so good. Any questions up to this point? But what does this mean? What is x? I mean, what is this sort of system? This is a homogeneous system, right? This is a homogeneous system. So this is a homogeneous system. This is homogeneous system. So that means that you can actually think of VPerp as a null space, right? Because remember, a null space was always a name that you gave to, to a system of homogeneous equations. So VPerp is actually a null space of what? Null space of a matrix A. And what is this matrix A in this case? What would be the matrix A? Well, you hopefully remember how to find the matrix. It's just like the coefficients that you see here is 1, 0, 1, and 0, 1, 1. So actually to find VPerp, we would have to find the null space of this matrix. And how do we find the null space of this matrix? I mean, this one is actually, it's kind of silly because like this one is already completely reduced, so you don't have to do anything. So I'll just like, there's no simplification that you can do. So you can, I mean, you can say that, like the next example I'll do, you have to simplify it a little bit, so it won't be as silly as this one. But in this one, it is like just as it looks very silly because it was like the matrix was already reduced. But so the idea here is that the null space is just is like the use equal to xyz, where x equals minus c and y equals minus c and z equals z. So it's c times minus 1, minus 1, 1. So what this is saying is that every vector in the null space is just, or every vector in VPerp is just a multiple of this vector. So every vector. So like in this in the picture that we had for this particular problem, you have the plane, you had this plane, which was like x plus y minus z equals 0. And you had these two vectors, v1 and v2. And v2. And what I'm saying right now is that any vector that's perpendicular to these vectors and every other vector in the plane had to be a multiple. This vector is a multiple of -1, -1, 1. So it looks like some sort of a line which is perpendicular to this plane. In fact, I can show you how that looks like on GeoGebra. So we have the plane, and then I'm saying that you have this vector u, which is -1, 1, and -1, 1. Let's see if I can change the color for this one to make it better. Right, so what I'm saying is that like you see, this green vector is perpendicular to the plane, and I'm saying any other vector that's perpendicular to the plane is a multiple of it. No, so as I said at the beginning of class, there's no quiz today. So yeah, I'll just give you like an assignment instead. Okay, so that is how the and by the way, this vector is what's called the normal vector to the plane. If you take multivariable calculus, this agrees with that. So if you ever take multivariable calculus and you find a normal vector to a plane, it's essentially this thing. Oh, here it looks nicer. Like maybe it's more clear that it has like a 90-degree angle. So you have to rotate it sometimes a little bit so that it's better, more. If you rotate the picture a little bit, it's more obvious. Sometimes like that the angle is 90 degrees. Um, but and that's kind of always the case. So, but let's just check what we did. So what did we do to find the complement, the orthogonal complement? What we did was to compute a null space of a matrix, right? But what was this matrix? This matrix, if you look at it, how does this matrix relate to the basis for V? Well, they are exactly the same vectors, right? I don't know if you see it here. Oops. How how could you obtain this matrix? Well, these are the rows are essentially the basis vectors for V. So if you had written this vector as a row, you get 1, 0, 1, which is the first one. And if you had written the second vector as a row, if you had written the second vector as a row, you have 0, 1, 1. So in other words, and that's actually what will always happen. So to find the complement to a vector space, you create a matrix whose rows are the basis for V, and the null space of that will be the orthogonal complement. So let me write that down because that's like the most important thing of what I have said so far. So here's like the way, the method to find V perp. So here V is a vector space with a basis consisting of the vectors V1 up to Vk. So what do? You create a matrix A whose rows are these vectors. So the first step is to create a matrix A. The important thing here is like this matrix has as rows the vectors. So the vectors are not written as columns. They have to be written as rows for this to work. And then the perp is just the null space of this matrix. So it's super easy. So again, this problem is just about finding a null space at the end of the day. So the perp is just the null space of A. And that's all. So this problem about finding the complement to a vector space is just a problem about finding null spaces. Okay, so let me show you, let me give you another example so that you see how this looks like. So here's another example. Let's say that V is a vector space with basis. Let's say I give you the basis for V already. Okay. So the question would be to find basis for, so the problem would be to find V perp and a basis for it. So what do you do? Will you do, so if you follow the steps that I told you, once you have the basis for the vector space V, the matrix that you have to form is just that basis but written as row vectors. So you can, let's put this one first. At least 1 second. So that's that is the matrix you have to work with. So again, the only thing that you have to remind yourself of for these problems is to write the basis vectors as row vectors. That's the only thing that you need to be mindful of. And so what is the perp? The perp is just the null space of this matrix. So how do you find the null space? You have to do the row operations, right? I mean, maybe let's just to make this more interesting. Sorry, let me just fix this. I mean, so that the problem is not so silly. Let me put a third vector. Oh no, because it has to be, no, let's just leave it like that, sorry. Okay, let's say like I have the basis here. Um, and then you reduce this matrix. How can you reduce this matrix? Like, let's just do minus row 1 plus row 2 into row 2. So you get 1 0 minus 1 2 0 0 0 3 5 0. Oh, sorry, that's good. This is 1, right? This is better. Yes. And then to reduce this, like you can do root 2 over 3 if you want. And we're almost done. Just add row 2 to row 1. Um, so what's the null space here? Again, usually I call the variables x, y, z, w. So I'll call this as x plus 7/3 w equals 0. And z that's what it is. And so this tells you that x is minus 7/3 w and y is minus 1/3 of w. So a vector in V perp, right? What does this become? Sorry, this is minus 7/3. It's not so clear, maybe. It is minus 7/3 w minus 1/3 WCW, and you break it into W and Z. So well, let's put C first just to follow it alphabetical order. I mean, not alphabetical order because obviously C is the last letter, but usually after 3 variables, you use W afterwards. So okay, so that's what it is. So the basis is the basis for VW, sorry, for VPerp. Let's call that U1 and U2. So let's use U1 0, 0, 1, 0 and U2 minus 7/3 minus 1/3 0, 1. And any other vector in V perp is a linear combination of these two. And any other vector. Okay. So what that means, so just to show you what this is saying. So okay. So V has basis. So what I'm showing you here is that V had basis V1, which was 1, 0 minus 1, 2. And V2, which is 1, 0, 2, 3. And we just found that VPerp had basis U1 equal to 0, 0, 1, 0, and U2 equal to minus 7/3 minus 1/3 0, 1. Okay, so what this is saying, what this is saying is that and you can check it, like for example, if you take the dot product of this vector with this vector, you get 0, 0. If you take the dot product of this vector with this vector, you will get 0. If you take the dot product of this vector with this vector, you'll get 0. If you take the dot product of this vector with this vector, is 0. So this vector is perpendicular to both of these vectors, and this vector is perpendicular to both of these. So if you take linear combinations of these vectors, because the dot product is distributive, the linear combination will continue to be perpendicular to any linear combination here. So this, like literally what this looks like, it's just like the picture is kind of hard to make because the vectors have 4 entries. So you cannot really properly draw this in 3 dimensions. But what this kind of looks like is some sort of like, you know, it looks like 2 pieces of paper which are like kind of mutually perpendicular to one another. So this is like a sketch of what's going on. But the important thing here is that you know, to find this, it's just finding a null space. So in terms of like what you need to do is the same thing that we have been doing all along. It's just that now you interpret the null space as a complement, an orthogonal complement. But besides that, there's nothing else that happens. So in fact, like this gives you, because like the vperp, since vperp is a null space of A, that actually gives you like a formula for the dimension of vperp, which is kind of useful to have. So the dimension of vperp is going to be the dimension of the null space of A, and that's just, if you remember, the dimension of the null space of a matrix was the nullity of A, and that's just the number of columns of A minus the rank. So, I mean, in practice, like once you find a null space, you will always see that this is true, but it is convenient to have like a specific like a formula for the dimension of the of vperp. So, um, so that is how you find the vperps. Why am I doing this? Like that will become more clear next time. When I tell you how to find like a projection matrix, but for now, I mean, it's just like, well, we're interested in vperp. I mean, you can define vperp, and it's convenient to do so. So, but yeah, for now, it's not so clear why you would work with it. But next time, I'll tell you why this is useful. What I wanted to do in the remaining time is something kind of related to this, which is called the Gram-Schmidt method. So let me tell you that. But first, I don't know if there are any questions so far up to this point. So again, like up to this point is what we did was find a null space, and that's all. Okay, so now let me tell you about the Gram-Schmidt method. What's called the Gram-Schmidt method. And what's the point here? So the idea is that like I don't know if like I have emphasized this enough. When you have a vector space, right? So let's say that V is a vector space. In general, V will have a basis, right? But the point of a vector space is that there's not a unique choice of bases. There are infinitely many bases for a given vector space. So it has a basis. But in fact, the choice of basis is not unique. And more and actually there are infinitely many choices for a basis, and actually there are infinitely many choices for a basis. Okay, so for example, we had, just to go back to the vector space that we worked with at the beginning of for earlier, a couple minutes ago, if you had V that was like the vectors that solve x plus y minus z equals 0, we saw that a basis for V, right? A basis for V was V1 equals 1, 0, 1, and V2 equals okay, I'll call this let me call this basis. I mean, this is the same vectors, but I'll call them W1 and W2 just for the moment. You'll see why in a second. Otherwise, again, it will be a little bit messy. So you have these vectors. The basis for this particular vector space would be these two vectors. But again, it's not that that is a unique choice. Okay. So for example, I mean, this is like a natural basis to find, but it does have a disadvantage. So this is like this basis W1, W2 is natural, but it has a major disadvantage. But it has a flaw, which is the following. These vectors, right? What are, like, let me ask you to see if this is making sense. Are these two vectors what are the vectors W1 and W2 perpendicular? Yes or no? What do you think? So if you do the dot product between W1 and W2, right? That dot product, what does it give you? It gives you 1, which is not 0. So these vectors, these basis vectors does not consist of perpendicular vectors, right? So W1, the flaw is that W1 and W2 are not a 90-degree angle. And I mean, again, like at this point, it is not so clear why that is a big thing, but it will be next time. It will be very convenient to next time. It will be very convenient to have like a basis vectors be orthogonal. So what we would like, what we want, is actually something like that looks like more like this. We want something where we want a basis. We want the basis, let's call it V1 and V2, that are at a 90-degree angle. So that's kind of the goal. Our goal is to find like a basis for V. The goal is to find a basis for V where the vectors are mutually perpendicular to one another. So the goal is to find a basis for V where the vectors are mutually perpendicular. And that's in general called like an orthogonal basis. So an orthogonal basis is a basis for a vector space where every vector in the basis is perpendicular to every other vector in that basis. So let me give you that as a definition. A basis for a vector space is called an orthogonal basis if every vector in the basis is perpendicular to every other vector in that basis. So like the vectors in the basis are mutually perpendicular. So the vectors in the basis. Okay. So again, you kind of want every vector in the basis to be a 90-degree angle. It's not so clear again why right now you want to do that, but next time you'll see it's kind of convenient to do that. So so the question is like, can you achieve that, right? So the main question is, can you always is that possible, right? So the question is, can you find an orthogonal basis for a vector space? And the answer is yes. And that's what the Gram-Schmidt process guarantees. So the answer is yes, it can always be done. Yes, you can always. In fact, you can always start. You can start with an arbitrary basis, and you can modify it to make it an orthogonal basis. In fact, you can start with a basis for V. And this process is called the Gram-Schmidt process. So Okay, so in the past, I mean, there is like a very geometric way to justify this method. The thing is like that is first, it requires a little bit of detour because it it is like a long process. Like the algorithm, if you explain it in a traditional way, it's kind of confusing. Let me see if I can find this. Where do I have my videos? Do, 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 do. So like yeah, if you have seen like the videos like for the reviews that I have sent you, they were just like the videos that I of like this class that I recorded in spring of this year. So like there is like a video that I mean one of the lectures I did this Gram-Schmidt method in a different way, which is kind of like the way that you will find in the book and in most textbooks. That and so you can watch that if you prefer. It's just that that way of doing it, it is a little bit messy, and there's like a more elegant way using Gauss eliminate Gauss Jordan or reducing a matrix. The trade-off is that if you're doing using in matrices, it's kind of not clear why it works, but it just I feel it's just better to have that because it's a lot more convenient in terms of computations. Explaining why it works would require like doing things that we didn't cover, like the LU decomposition of a matrix. So I'll just tell you what the method says. But I mean, there is like a more geometric way to justify the this process, and if you want to watch it, I mean, you can. But what I'm going to give you is a lot better in terms of like actually finding the answer. So it is more like organized than like the usual approach that you'll find on the book, for example, or even online. So I'm going to use it like using matrices. It's just like it's a little bit of odd, or like it won't be clear why this works, but like I feel like that's okay just because it is a lot more like less messy. So I'll tell you the method. It would be like a black box. It's like an article of faith, however you want to think about it. But it is like I'll give you the method in using matrices. It's just so fast, or that it is worth. So there's like an alternative way to do it that is better. It's very easy to memorize this algorithm. So in the usual Gram-Schmidt method, like if you try, it's very complicated to memorize all those formulas. So it just takes two steps basically. You make a matrix A whose rows are the basis for V, so whose rows are the basis vectors you have for V. And then you reduce you reduce the system or the matrix. So it's only two steps basically. Uh, well, let me break it into three steps. So you compute the matrix A transpose, and then you reduce the matrix A transpose augmented with A until A transpose becomes upper triangular. And when reducing this matrix, the only thing you'll see, like I'm about to do some examples for you so that you see how this looks like. The only thing when you do this is that when reducing this matrix, if you remember, like we have 3 row operations. When reducing the matrix, we're only going to use one of those 3. The only one that we're going to use is like the operation of combining rows. So when we're reducing the matrix, but that's fine because we're not trying to reach the identity. We're just going to try to reach like an upper triangular matrix. So you'll see it is very simple. I'll show you what happens. So when reducing the matrix, only use the operation of adding rows. So do not use the operation of switching rows or multiplying a row by a scalar. So do not use. So it is actually faster than like the usual row reduction because there are fewer operations to do and we're not trying to get to the identity. So it will take less steps. And so the point is that the idea is that you started with A transpose, A, you're going to get something that's upper triangular. And here you get like to a matrix, and this, whatever you get here will be the matrix whose rows are orthogonal. Matrix whose rows are orthogonal vectors. And this will give you the basis for the orthogonal basis that you are after. And these will make up the basis. So again, I'm about to give you a couple of examples. In practice, like many times with linear algebra, the algorithm sounds more complicated than it actually is. Once you see it in practice, it is not too bad. But like if you just write it out, it is maybe a little bit more confusing what's going on. But you'll see once I give you the algorithm, it is actually not too bad. Sorry, I just gave you the algorithm, but I need to give you some examples. Once you see the examples, you'll see that finding the orthogonal basis is actually pretty simple. So let me give you a couple of examples. The first one, like let's say that V was this thing that we have been working with, like x plus y minus z equals 0. So we knew that a basis is okay. So this is the example we have been using all along up to now. Sorry, this was 0, 1, 1. Oops. So now the question would be to find an orthogonal basis. Okay. Would you give me a second? Sorry. So it's very simple. You make a matrix whose rows are these vectors. So it's kind of like the same as before when we were finding the V-perp. So the good thing here is like both methods you require the same matrix. So you make a matrix whose rows are these vectors. So let's say 1, 0, 1. That's the first one in here. And then the second one would be 0, 1, 1. Okay. So that's the matrix that you have to work with. And then you consider A transpose. What is A transpose? It's 1, 0, 1, 0, 1, 1. And then what is the transpose of this matrix? I mean, again, remember the transpose just turns the rows into columns. It's this. So this is 2 by 3, and this is 3 by 2. So you're going to end up with a 2 by 2 matrix. What's a 2 by 2 matrix you end up with is what? If you do the dot product, I mean, remember the matrix multiplication is actually doing a bunch of dot products. So you get something like this. All right, so this is what A transpose is. And so the method says, take this matrix, right? Take this matrix and put a vertical line together with the matrix A. So that gives you 2, 1, 1, 2, and then A is, let me put it in colors, 1, 0, 1, 0, 1, 1. So that's a matrix A. So this is again A transpose, and this is A. Okay, and now instead of trying to get to the identity, now the point is that we're not going to get to the identity here. That's not the idea. It's just to get to an upper triangular matrix. So what does it mean to get to an upper triangular matrix? It just means that the non-zero stuff can only be here. So the stuff below the diagonal has to be 0. So essentially what this is saying is that we have to put a 0 here. Okay. So we need to make this entry 0, and that's all. Make this 0. So it's only going to take us one step, literally. It's just that the only difference with the previous reductions we have been doing is that in this case, the only operation that you are allowed to do is to combine rows. So you're not allowed to switch rows. So you cannot do row 1 with row 2. You cannot switch them. And I mean, you could kind of multiply by a scalar, but also we don't need to do that. So like the only thing that we're going to do is to combine the rows together. So of the 3, it's only one operation. So we can add a multiple of one row to another row. So how could you get a 0 here? Well, you could do -1 row 1 plus row 2 into row 2. Because if you multiply this by -1/2, this will become -1. And when you add it, you get 0. And that's all. So let me put in blue what you get. So -1/2 with 2 gives you -1, so that gives you 0 here. And then let's see, -1/2 here with 2. Okay, so you get 2 -1/2. Maybe I should put it here. So this is what the entries look like. Okay, after you do that operation, it's 1 -1, 2 -1/2, -1/2, 1 -1/2. Okay. And so if you look at this gives you 2, 1, 0. What is this? 3 halves. And let me put a different color here. And what's the nice thing here? The nice thing here is that this is already upper triangular. Right? This matrix is already upper triangular. So nothing else is needed. So so what the method says is that the vectors that you get at the end, on this end, are the orthogonal vectors for the vector space. So what I'm saying is that this row and this row make up the orthogonal basis for V. So let's call them V1 and V2. So V1 being 1, 0, 1, and V2 being minus 1/2, 1, 1/2. If you look, you can check the dot product between these two vectors is 0. Okay, the dot product between these two vectors is 0, and so they make up the orthogonal basis for V. So, in fact, I can show you how they look like on GeoGebra. Let's see. Let's see. I think I cannot erase this. Perfect. I can show you this. Let me go to GeoGebra. Just a second, so that you can see this. It's kind of cool. So again, originally our basis for the plane, right? Our basis for the plane were these two vectors, 1, 0, 1, and 0, 1, 1. If you notice what I wrote, I'm going to keep the first one, 1, 0, 1. So let me put that one in green. And now the second one is not perpendicular to the first one, right? The angle is not 90 degrees, so that needs to be fixed. So to fix it, I'll just erase it, and I replace it with this vector, which we just found, like minus 1/2, 1, 1/2. Okay. And this is the one that was in pink in my picture. So you see it is, let's see, I can make this a little bit cleaner. Okay. I don't know how clear it is that these two vectors now make up a 90-degree angle. So you kind of, like, what you did is kind of fix one of the vectors so that they would become perpendicular. So that's what the Grant-Smith process does. Like it can, because again, like this was the original vector. You see, like these were like the two original vectors, right? And keeping the green one and replacing the black one with the pink one. And so I made them perpendicular. Okay. Again, it's kind of magical, mystical why the method works, because I didn't explain that, but it's just a lot better to do it that way than with the usual approach, like, because it's just like a huge number of formulas and, like, yeah, it's a little bit tricky. So, but this one instead is like very, very simple. So I'm about to give you another example, which is a little bit more complicated, but you'll see it's always the same. But it's kind of like nice to see it happen. Is that making sense? Let me see if I can. Okay, so now here's another example. Let's say I give you let's say I give you this vector space that has a basis. Let's see. Okay. And so what I want now to do is to find an orthogonal basis for B. Let me call these vectors W1, W2, W3. So what we will do is to so how do you make an orthogonal basis? Again, you make a matrix whose rows are these vectors. So that's the important thing. So the first one, this is the first row. Here's the second row. Minus 2, 3, 0, 1. This is the third row. 1, 1, 1, 5. 1, 1, 1, 5. Okay, so that's the first step always. So step one is just to construct this matrix. Step two is to do A transpose. So let's do A transpose. So you do 0, 1, 0, 1, minus 2, 3, 0, 1, and 1, 1, 1, 5 times A transpose, which will be 0, 1, 0, 1, minus 2, 3, 0, 1, 1, 1, 1, 5. Okay, so what is this matrix? This is 3 by 4. This is 4 by 3. So actually you end up with a 3 by 3 matrix. Let's check. So what happens if you do this with this? You get a 2 in the first entry. When you do this one with this one, you get a 4. Oops. When you do this one with this one, you get 1 plus 5, 6. Okay, and then and then the other ones are similar. So let's see, like this one with this one gives you 3. It gives you 4 again. All right, because it's symmetric. And then this one with this one gives you 4, 9, and 1. That's 14. And then this one with this one gives you minus 2 plus 3. That's 1 plus 5. So you get 6. And then you get you get a 6 here. Oops. You get 1 and 5, 6. And here you get what do you get here? You get minus 2 plus 3. I mean, you get a 6 again. And the last entry is a little bit bigger. It's 1 plus 1 plus 1. So that's 3 plus 25. That's 28. Okay, so that is what the matrix A transpose looks like. And again, you consider A transpose together with the matrix A. So what does that give you? It gives you 2, 4, 6, 4, 14, 6, 6, 6, 28. And this gives you the matrix 0, 1, 0, 1, minus 2, 3, 0, 1. And then 1, 1, 1, 5. Okay, so that's yeah, that's the matrix. So again, this is A transpose, and this is A. And the goal is to make this upper triangular. So you want a 0 here, you want a 0 here, and you want a 0 here. So basically, the only thing that can be non-zero is this stuff. So again, it's faster than just getting to the identity because we don't have to fix all the entries. We're just trying to get to an upper triangular matrix. And the only operation that we're doing is just combining rows. So you basically have to put like a 0 here and a 0 here. And that is perceived more or less in the same way. So you can do minus, like, let me use some different colors. So you can do minus 2 row 1 plus row 2 into row 2. And we can also do minus 3 row 1 plus row 3 into row 3. And so let's see what that gives us. So it will give us 2, 4, 6, 0, 1, 0, 1. Okay. And so this will become 0, right? When you do minus 2 here, you get 8. So, sorry, minus 8. So 14 with minus 8 gives you 6, right? Then this becomes minus 12. So minus 12 with 6 is minus 6. And then what you get here, you get minus 2. Then this is minus 2 with 3 is 1. This one is 0. And then this one is minus 2 with 1. That's minus 1. And then this is the last one is 6. It became minus 6 with 6 is 0. Then this is minus 12 with 6. That's minus 6. And then this is minus this is minus 18 with 28. That's 10. And then this gives you 1. Then this one is minus 3 with 1 is minus 2. Then 1 and then 2, if I'm not mistaken. Okay. And we're almost done. Why? Because again, the goal is just to get to upper triangular. So there's only one more coefficient to take care of, and that's can be taken care of by doing row 2 plus row 3, and that's it. So you don't have to fix this one because the goal is upper triangular. So there's no need to do anything else. Let's do minus row 2 plus row 3 into row 3. So you get 2, 4, 6, 0, 1, 0, 1, 0, 6, minus 6, minus 2, 1, 0, minus 1. And then this gives you, when you add the second row with the, sorry, it's just adding them, right? Like you don't even need to do minus row 2. You just do row 2 plus row 3. So when you add them together, you get 0, 0. You get 0, 0, 4. And then you get minus 1, minus 1, 1, and 1. Okay. And this is upper triangular. This matrix is upper triangular. So you are done. So what that means is that these 3 rows are the orthogonal bases for the vector space. So V1 0, 1, 0, 1. V2 is -2, 1, 0, -1, and V3. I mean, you could write, I mean, I guess you could write them if you prefer as column vectors. That's really not too much of an importance. So forms the orthogonal basis. So again, the point is that if you, for example, do the dot product of this with this, you get 0. If you do the dot product of this with this, you will also get 0. If you do the product of this with this, you'll get 0. So all the possible dot products that you could make between these vectors will become 0. So the vectors became mutually perpendicular. Okay. So again, like this algorithm is kind of like not clear why it works, but it just happens to work. But it is like a nice way to kind of find the orthogonal basis. So what we would use that for next time, as I said, like we have very few topics left, like in the class. I probably need like maybe like 3 more hours or two of material, and then we're done. Then we'll just do review session. But what we'll do use that next time is that once you have an orthogonal basis, you can get to an orthonormal basis very easily. That just means that the vectors will have length 1 in addition to being mutually perpendicular. And once you have that, then you can find like a projection matrix, which is a nice thing to find. So I'll show you what that is works like in next time. But this is like kind of like almost a lot important algorithm for the exam, because everything else is kind of like very strict, simple consequence of this. But yeah, like there are very few topics left, but we should be able to finish it like in, I would say, 1.5 classes or one more class. So I'll tell you more about this. Yeah, so I'm thinking I'll put it on the study guide, but between 8 and 10. So you'll have more time for the final. The final, basically, I was going with like 2 parts of 80 minutes each. And so each part would have like 4 or 5 problems, basically. So it's quite like so you will have like, usually the midterms have been scheduled from 8 to 10. The final is like officially scheduled from 8 to 11. But I'll do like 2 parts, 80 minutes each. So, but yeah, I don't want anything. It won't be too long. So it will be like 4 or 5 questions, yeah, on each part. So that's kind of it. Well, that would be at most 10 questions because it's only 2 parts. I should try to grade them by tomorrow. I was finishing writing the study guide for the final so that I could send it. Uh, um, yeah, I think I should be able to have like the first part ready today and like the second part tomorrow. But I mean, yeah, sometime tomorrow I should finish grading the exam. Um, but yeah, I can send you the solutions. I mean, I prefer to send the solutions once I finish all the grading. But yeah, I'll give you all of that by tomorrow at some point tomorrow. Yeah, yeah, if that sounds good. But yeah, I'll start the grading sometime today for the first part, and I think that I should be able to finish the first part today, and then do the second part tomorrow. Okay. But yeah, I'll see you. Okay, so I'll send you like the announcement and the summary of today. But yeah, next time I can tell you more information. Okay, see you. Bye. Have a good one.